Okay, let's get going. Okay, so welcome again to the Oxford Discrete Maths and Probability Seminar. So it's a great pleasure to have Asaf Ferber, who's going to talk on lower bounds and multicolor Ramsey numbers.
Okay, so thank you for the invitation. So let's start. So today I want to talk about lower bounds for multicolor Ramsey numbers. This is a joint work with David Conlon, which is a former Oxford faculty and is now in Caltech. And so hopefully I will be able to show you the entire proof. It's a relatively new and quite short result. So let's start. And I'm not sure about the audience, how many students you have, like undergrads or grad or whatever. So just stop me if I'm too fast with definitions or something. If it's something is not clear, so just feel free to ask questions, okay? Let's start with the most basic definition in the area is the following. Defined RTL. This is the multicolor Ramsey number, which is the minimum n, the minimum integer n, positive integer n, such that for every L coloring of the edge set of the complete graph on n vertices, there exists a monochromatic copy of KP. Okay, and then L coloring, let's start slowly. So an L coloring of EKN, we just mean like it's some function from the edges of the complete graph on n vertices, let's say to the numbers, it will be convenient for me to use 0 to L minus 1 instead of 1 to L. Okay, so this is an L coloring, and the monochromatic copy of KT is just that all the edges spanned by some specific set of T vertices are of the same color. So there are some examples which I guess that everyone knows. For example, let's consider the Ramsey number of triangles and with two colors. So the Ramsey number for this thing is 6, right? This is easy to show. So to show that if we have 6 vertices, a two coloring of K6, there is always a monochromatic triangle. This is an easy exercise. And to show that it cannot be something smaller, we can just draw some example on 5 vertices. And take the following two coloring. Okay, so this is a two coloring of the complete graph on 5 vertices without any monochromatic triangle. A little bit harder is to show that R for 2 is 18. Again, you need a lower bound, you need to find some construction of 17 vertices with two colors that has no monochromatic copy of K4, and to show that every graph on 18 vertices and more, like if you have two coloring of it, so you must have a monochromatic copy of K4. And this case, so far all the examples that I gave you are just for the case L equals 2 for two colors. And the L equals 2 is arguably one of the most famous problems in combinatorics. And somehow, like quite amazingly, I don't know, at least as a student, I remember the first time that I saw it, I said, okay, come on, it cannot be a problem. The first case, which is unknown, is actually R5 too. And the Ramsey number of a clique of size 5, two colors is unknown. I think, I forgot to check Wikipedia before the talk, so I think it's between 43 and 48. I'm not sure. So this is open. And because it's quite hard, if it's open for 5, clearly it will be much harder to try to determine the Ramsey number of a clique of size 100. So we are curious about some kind of upper bound, like general upper bounds. What if we take t to infinity? What is the growth rate of this function? And known bounds are the following. that are t2. On one hand, it's smaller than 4 to the t. On the other hand, it's larger than square root of 2 to the t, up to smaller order terms that I'm not writing here. And these bounds are known from the 1940s, both of them. Best known upper bound. So before that, the previously best known upper bound was due to David Conlon, and quite recently, an amazing student, like actually was an undergrad in MIT, managed to improve David Conlon's bound. Ashwin Sasot best known bound is due to Ashwin. And for the lower bound, best known lower bound is of order 1 plus little o of 1 times t times square root of 2 over e square root of 2 to the t. So you see that people really try to fight it. And actually the original bound was, I think, 2 over e. I think this was the original bound. So we just slightly managed to improve the constant. Now, unfortunately for the two colors, I don't have any news, but we can ask the same question. What if we try the three colors case? Okay. So let's try to understand what is known for the case where L equals 3. So if L equals 3, so in general, for every L, we have the following upper bound. L to the LT, which is basically follows from the same proof to prove the upper bound of 4 to the T for two colors. So the same upper bound holds also here. I can just write for every L, which is at least 2. Okay. So this upper bound is just like a simple induction. And let's do the L equals 3 case for a lower bound. So in case that L equals 3, we can show, and I will show you in a second, that it's at least square root of 3 raised to the t. And the proof is essentially the same like the proof for two colors. Okay. And for L, which is larger than 3, so there is a nice trick due to Lefman that he showed how to boost it. And he proved that the Ramsey number of T with L plus L1 plus L2 colors, I'm cheating with -1 plus 1s, okay? Is at least the Ramsey number of T and L1, it should be -1 everything, and the Ramsey number with L2, okay? So basically what you need to do, you just want to blow up. So I can just write here a hint. This is a simple exercise. Just blow up K RT L1 to K RT L2. Okay, each vertex, just replace each vertex in such a complete graph in a copy of K RT L2s and just color it accordingly. And so what I want to show, so these bounds are the best known bound, at least for L equals 3. Apparently for L equals 4, like after writing our paper, we realized that theoretically could do slightly better anyway. And for L equals 3, these are the best known bounds. And what I want to show you today is how to slightly improve the lower bound. So a theorem. So we show the following, that R T3 is at least 2 to the 7t over 8 plus little o of t. And RT4 at least 2 to the t over 2 times 3 to the 3t over 8 plus little o of t. Okay, and using these two bounds, we can get an exponential improvement for all L's which are at least 3. And just to compare the bounds, comparison. So before that, the square root of 3 is roughly 1.732, and we improved it to roughly 1.834. And for L equals 4, so we add, for L equals 4, the lower bound, I could just write the lower bound here. In general, it's just like RTL, square root of L raised to the T. So for 4, you see the lower bound is 2 to the T. This is for L equals 3. For L equals 4, we improved from 2, we improved to 2.135. Okay, so we have an exponential improvement for all number of colors, which are at least 3. Okay, and very interestingly, so our construction for L equals 2 for 2 colors, it gives exactly the same bound like what you get like in a random graph, right? So we're not really losing there, but we don't gain anything. Even we try to analyze it and you even get the correct constant, like everything is just exactly the same like in the random graph. Any questions so far? No? Okay. So let's start with a kind of a warm-up, which is a proof that I guess that most of you are familiar with. But I think that it will just emphasize like the main idea behind the proof is like, so I think it's nice to see it once again. So lower bounds, I will focus only on the 3 colors case, and the rest you will just see that you can just do the same strategy will also work for 4 colors. So let's consider the case L equals 3. And I want to give you the first lower bound, the square root of 3 raised to T. Okay, so this is my goal. Okay, and the way that we do it, we just take a random coloring. So the proof, just take random C from the edges of complete graph on n vertices, and will be chosen soon to 0, 1, 2. And we see that the probability that there exists an I monochromatic KT is upper bounded just by the union bound, is upper bounded by n choose T times 1/3 raised to T square over 2. Okay. And if we can choose it, if we can choose n in such a way that this is smaller than 1/3, right? So if, then we are done. Then we are done, because then we see that the probability that there exists some monochromatic clique in one of the 3 colors is smaller than 1. In particular, it means that there exists a good color. Okay, so this doesn't give the correct constant, but it gives the correct asymptotics. And if we analyze it, so we see that this is exactly what we get, because we can upper bound this expression by En over T 3 to the T over 2 raised to the T. And we see that this expression is smaller than 1/3, or actually much smaller than 1/3, if we take n to be slightly larger than 3 to the T over 2 times T over E. So sorry, slightly smaller. We can say we see that you can take n to be roughly 1 plus little of 1 times T over E times 3 to the T over 2. Okay. And this gives us the lower. So we see that E. Okay. And same thing work for every number of colors, right? You just need to divide, like instead of 1/3, you write 1 over L raised to T square over 2, and this gives us the square root of L raised to the T. And as in all of these probabilistic arguments, probably the lossiest part is the union bound, is n choose T. And therefore, what we want to do is to try to come up with a coloring which is hybrid, meaning that first of all, we do something that takes care of as many clicks as we can. And then the remaining bad spots that we'll see in a second that will make it more clear, we want to color at random with the hope that now we need to union bound over much, much less subsets. Okay, so the idea is quite simple. And let me lead you through slowly. So now I want to improve it. And before showing you our improvement, just not to take all the credit and show that this is based on some problem that hopefully all of us know. And even if one person in the audience doesn't know it, so I think it's worth it to go over it because it's a nice one. So let me write a toy problem. Actually, it's toy problems, 2 problems. Sorry. So the general problem is the following. Imagine that we have some town, and in the town we have T citizens, and we wish to form clubs. Okay, what is a club? It's just a subset of citizens. They are not necessarily disjoint, okay, but they must be distinct, such that first, every club CI is of an even size. And 2, every 2 distinct clubs have an even intersection. Okay, so this is toy problem 1. And the question that as combinatorialists you are interested at is what is the maximum number of such clubs that you can form? What is the largest family of such clubs that you can form? The max number of clubs satisfying 1 and 2 that we can find. Okay. So if you don't know it, can you try to guess what should be like at least a lower bound, a decent lower bound? No? Can you do exponential? Okay, so I guess that the Oxford students are just shy. So let's see. So just for a lower bound, what can we do? We can take the T citizens and we can just pair them up. Okay, can just pair them up into T over 2 pairs. And then for each pair, we can just decide like for each pair as one individual, right? Like every time I just want to decide on each pair whether I want to include both of the pair, the citizens in this pair or exclude them. So clearly I can find such a collection of 2 to the T over 2. So this is a lower bound of 2 to the T over 2. Again, I assume that T is even, so forgive me for small mistakes, okay? So we can easily obtain a lower bound of 2 to the T over 2. And something which will be important for me also in the construction. So this is not very hard to show that this is also the upper bound. For upper bound, we need to work a little bit harder, but again, it's not too complicated. What you want to do the following. So imagine that you manage to come up with a family of clubs, F, okay? It's like C1 up to C whatever. And I want to show you that this set is not too large. Okay, again, it's exponentially large, but it's not 2 to the T, okay? So what can we do? We can think about each club. Okay, I'm going to think about it as the characteristic vector of the set, and I'm going to walk over Z2. Okay, so think each CI, we can consider it as a vector in Z2 to the T, the characteristic vector of CI, that in each coordinate J, it's a 1 if and only if the Jth citizen is in club I. And then we can define V a subspace of Z2 to the T to be the span of all these vectors in F. And what's the main observation? The main observation is that by definition, so what do we know? We know that each club is of an even size. It means that the inner product of every club with itself is 0 mod 2. And also the intersection of every two is even. So also the intersection, the inner product of every two clubs is 0 mod 2. So what's the main observation is that V is a subspace of the orthogonal complement. I'm not sure that it's legal to say orthogonal complement over a finite field, but hopefully you understand what does it mean. So V is a subset of its orthogonal complement, is a subspace. And from the rank nullity theorem, we know that T is the dimension of V plus the dimension of the orthogonal complement. And because V is a subspace of the orthogonal complement, so this is at least 2 times the dimension of V. So it means that the dimension of V is at most T over 2, and therefore clearly the size of the family, which is clearly upper bounded by the size of the subspace, is at most 2 to the T over 2. Okay. So what do we know? We know that if we have such a scenario, so we can have at most 2 to the T over 2 many clubs such that each of them is of an even size and the intersection of each 2 of them is of even size. Now let's switch to toy problem 2, which is basically going to be our main gadget. So toy problem 2 is just I want to change the rules. So the first one, I still want that every club will be of an even size. And the second requirement, now I want that the intersections will be of an odd size and not even. For every I not equal j, Ci intersecting Cj, I want it to be odd. And we can ask the same question. Is the max size of such collection? And here, perhaps surprisingly, perhaps no, the answer is that it's upper bounded by T. Not exponential, polynomial, it's at most T. And the idea is quite simple, because if you think about it, these two restrictions that the inner product of each club with itself, if I think about it as a vector, is 0 mod 2, and the inner product of every 2 is 1 mod 2, this forces the vectors to be linearly independent over Z2 to the T, and therefore we can have at most T of them. So hint, 1 plus 2 implies that the vectors C1 up to Cn are linearly independent. Okay? And this is going to be our joker in the sense that now we have a coloring that takes care of cliques in one color. So let me describe the construction. So I aim, okay, so the goal is to define a two coloring from the edges of a complete graph on n vertices to 0, 1, and 2. Okay? Actually, maybe it will be easier for me. I made a mistake. Maybe it's better to write 1, 2, 3 here. Just write 1, 2, 3. It will be a little bit more natural. So this is my goal. What I'm going to do, I'm going to look at probably more vertices, right? I'm going to color a complete graph on more than n vertices. And then I'm going to take a random a random sample of n vertices out of this graph, and I want to show that this coloring, the induced coloring, is already a good coloring with high probability. So let's start slowly. I start with a set V. I'm not going to tell you okay, I'm not going to tell you what's the size, but it's going to be all the vectors. So V here is not going to be the vertex set of my graph. Okay, it's not like the size of V is not going to be n. So V is all the vectors in Z2 to the T such that the inner product V with itself is 0 mod 2. In other words, let's go back to this toy problem, is just all the clubs of an even size, no restrictions on the intersections, okay? So this is easy to show that the size of this set is exactly 2 to the T minus 1. So I will just treat it as 2 to the T, okay? Because we don't care about these small constant losses. So I can think about V as Z2 to the T, but it's important for me that it's only vectors such that the inner product with themselves is 0, like self-complementary vectors. And now I want to define the coloring of pairs in V. It's still not the coloring of the complete graph on n vertices, because V is assumed to be like 2 to the T is assumed here to be larger than n, my target n. So define C from V choose 2 to 1, 2, 3 as follows. C of a pair UV, unordered pairs, is 1, as you can guess, if the inner product is 1 mod 2. And otherwise, just color random. 2 or 3 uniformly at random, otherwise. Okay? And now to obtain our coloring, so just take n random elements from V. Okay? Now, let X be a subset of V of size n, again, uniformly at random. And then our coloring is just C restricted to X. Okay? So that's what we want to do. This is the construction. And now we want to analyze it and show that it gives us an exponential improvement. Any questions? Right? Hopefully it's simple enough. And so as you can guess, like from the toy problem, we already know that with this color, we have nothing to do, right? Because like we took only vectors, U and V, such that the inner product with them, like UU and VV, like let's call it their norm is 0. And if their inner products are 1s, so we know that it forces such a collection to be linearly independent, right? So every one monochromatic clique consists of linearly independent vectors, so we cannot have more than T. Okay? So let's try the analysis here. So color 1, this is just the even odd down problem, right? So just max clique of size at most T. Okay, and again, I'm not careful here with T plus 1, T minus 1, okay, sorry. And for the other colors, we need to be a little bit more careful. So let's see how to do the analysis. So because it's random, I just want to show that actually we saved quite a lot, and then we just take a simple union bound. But in order to show that we saved quite a lot, I want to show that we can actually count everything quite precisely. So let's see. What does it mean that we have, let's say, a 2 monochromatic clique or a 3 monochromatic clique? So I can scroll up and imagine that before the uniform at random, just imagine that I use 2 colors 1 and 0. Okay, like either according to the inner product, it's either 1 or 0. So with the one color, I'm already all set, like I have nothing to do. I'm already like, and what is nice, how can you see that it's a save? Because you see that we already colored like half of the edges have been colored, right? And we took care of all these clicks, so it looks like that it's the correct proportion, right? We colored like half of the edges. And that's why at the beginning I thought that maybe there is some clever way to do it, to make it work for two colors. You see, we took care of half of the colors. If you think about it, so here the coloring is quite strange, because with color 1 we have half of the colors, but 2 and 3, each of them is going to occupy roughly 1/4 of the edges, right? So it's not a balanced one, which I think it's a quite nice observation to show that something here we didn't do correctly, right? Like there must be a better way to look at it. But unfortunately for two colors, we just couldn't. We tried to recolor, we tried to do many other things. But let's see, so for color 2 and 3, if we think about this auxiliary color 0, so which subset of vectors can be monochromatic 2 or 3 is just what is called this even club, right? Like blah, 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 many vectors such that the inner product of every 2 of them is 0. So this is called the potential clique. So let's say that a set X subset of phi is called the potential clique. If and only if it's a potential clique, meaning that all the inner products are 0 mod 2. For every X and Y in X, we have that the inner product is 0 mod 2. Okay? Let's even say like, so here I cleaned up all the argument because I already work with the same T. So let's say a potential clique X of size T. The initial observation that we had, I can tell you at the end, like how did you came up with this diagonal? Like we had another observation that I thought that it was nice enough. And then we managed to push it to the diagonal case. So a set of size T is called the potential clique if the inner product of every 2 elements there is 0 mod 2, and this is of size T because this is our target. And just saying a potential clique is not enough for me for counting, because if I want to try to count, let's try to do it together. Imagine that I don't give you any other any additional information. So how many potential cliques do we have? So what can we do? So first of all, you want to choose a vector, right? Let's call it x1. So we have 2 to the t many options, right? At most. Now I want to choose a vector x2 such that the inner product of x2 with x1 is 0, right? So how many such options I have for x2? This is not a tricky question. Okay, so we'll help you at most 2 to the t minus 1, right? Because we want that the inner product will be fixed. We're just trying to solve some linear equation, right? And now just think about it. So we have a matrix, a 2 by t matrix, and I want to find an x3 such that this product will be 0, 0. So this is already a tricky question now. How many solutions do I have to this system of linear equations? And the answer should be, it depends, right? It depends on what? It depends on the rank of the matrix, okay? So it means that I cannot just start counting it like in a straightforward fashion. I need to assume something about the rank. So let me erase it. So for each potential clique, so we can define, let's write R, you just pick the rank, like given a potential clique, okay? So for each potential clique, I just want to characterize them according to the rank of the span of X, or the dimension of the vector space spanned by the vectors in X. And if I look now, I can try to count the number of potential cliques of rank exactly R. Okay, so let's try to count it. Number of potential cliques of rank R. And then we will optimize, we will just choose the worst case R is at most, and now we can just do the counting because it's quite simple now. So for the first one, we have 2 to the t many options. So let's imagine that the first R vectors are assumed to be linearly independent, okay? So the first one, we have 2 to the t many options. For the second one, 2 to the t minus 1. Third one, 2 to the t minus 2, etc., etc. So for the first R vectors, we can just write product 2 to the t minus I, where I runs from 0 to R minus 1. This is just to choose the vectors x1 up to xr, okay? Times, for the rest, what do we need? We need to find vectors which are in the span of the first R vectors. And so we don't need to solve this linear equation anymore because we also don't know how many solutions, but just to find something in the span. So there are at most 2 to the R, actually exactly 2 to the R vectors in the span of the first R vectors. So we can just write 2 to the R times t minus R, because we still need to choose t minus R many vectors. Okay? So this is an upper bound for the number of potential cliques of rank R. So let's calculate it. This is precisely 2 to the t minus R choose 2 plus RT minus R square. Okay? And this I can write it, if I ignore smaller order terms, we can write it as 2 to the TR minus 3R square over 2 plus, actually I can write it exactly, plus R over 2. I made a mistake, right? It's RT. It's 2RT. I made a mistake, right? From the first time, 2 to the t minus I, the product from 0 to R minus 1, it's RT minus R choose 2. I made a mistake. So this is exactly what we wrote. And now I want to optimize. So let's just define a function of R, because I'm not sure which R is my maximizer. So we can just look at 2TR minus 3R square over 2 plus R over 2. It's a very simple function. You can just take the derivative. And then we obtain 2t minus 3r plus 1/2. And therefore, you see that this function, if you try to solve it, the function f is monotone increasing all the way to r equals 2t over 3. So theoretically, plus 1/6. But because, so you see that the maximizer in theory is 2t over 3. But because this set is a subset, it's an even, it's a collection of even clubs with intersections which are even, and we saw that the dimension cannot be more than t over 2. So basically, the maximizer is r equals t over 2. Okay, and if you take r equals t over 2, you obtain the upper bound of 2 to the 5t square over 8. Right? Just plug into this expression r equals t over 2. Okay, but also the 2t over 3 also gives us an exponential improvement, but it's just like a small observation that in theory, like the maximizer is not 2t over 3 just because you don't have such a set X with rank 2t over 3. Okay, so now let's try to complete the proof. So we know that the number of potential cliques of any rank, right, is at most 2 to the 5t square over 8, up to smaller terms, okay? We know that the probability for a potential clique X to be monochromatic is around 2 to the minus t square over 2, right? Plus little of, here it's little of t square, so big O of t, right? So we know that the probability that the potential clique will be monochromatic is around 2 to the minus t square over 2, right? Basically, you just need to choose the color and then 2 to the minus t choose 2. This is what the little of t squared are. And we also need to do the sampling. We know the probability of X to survive. Say to survive is to survive the random sampling of n vertices is around n over 2t to the t. Okay, this is a small cheat. I just assume that we sample everything independently, but then you not necessarily have exactly n vertices, but it's easy to modify it. And if we want to combine everything, so all in all, the probability to have a monochromatic KT is at most number of potential clicks times 2 to the minus t square over 2 times n to the t over 2 to the t square. And this equals 2 to the minus 7 over 8 t square times n to the t. And we want it to be smaller than 1. Okay, so it's clear that if we take n to be slightly larger than 2 to the 7/8 times t, then we are good. Okay, and as I promised, so this completes the proof. So this is the entire proof. And okay, and it took me also like 43 minutes. I thought it would take me 40 minutes, sorry. Any questions?
So Asaf, thank you for a lovely talk. If anyone has questions, please do interrupt and ask, or ask in the chat. Actually, so one question, do you think there's any chance it can be kind of massaged, tweaked to get further improvement?
So for further improvement, so I'm not sure, because I at the beginning I was sure that it's going to give also the two-colors, but now I'm not sure. We played with it quite a lot. And also like the more embarrassing part is that now I even stopped believing that something like that can help in improving the Ramsey numbers for hypergraphs, right? Because if you think about it, just look at the calculations that I did. So we had, let me share the screen again. Like we didn't actually gain anything in the order of magnitude, right? Just in the constant, because you see, if you start with 2 to the t, let's imagine that our n is 2 to the t, right? If this is really our number of vertices, so how many potential clicks of size t you have in a random graph? You have roughly 2 to the t square, right? It's n choose t. And here we just gain something in the exponent, we gain like a small constant here, not something better. So I don't even see how to gain for hypergraphs. And also like it looks like that you should be able to come up with something better just because of this silly observation that this coloring is far from, I don't know, like at least I believe that for an example, for some good construction for a Ramsey graph, the colors should be more or less balanced. So this example is not balanced, right? Color number 1 captures roughly half of the edges and the other capture roughly 1/4 of the edges, right? So even though at the beginning I thought that, oh, now we have some idea that probably we can just improve all the non-bounds, now I start being a little bit more pessimistic. And I think that it was just pure luck that was tailored for this specific problem. But maybe I'm wrong.
I have a question. You've used that the rank R subspace has to be orthogonal to itself, and you've just used that there aren't any when R is bigger than t over 2. But presumably, you must have tried bounding the number of them. So when R is a bit less than t over 2, the number of these spaces doesn't sort of go from all rank R subspaces to 0. It decreases in some way, and that looks like it should.
I see.
Improve the constant.
So you want to try to somehow take care of these maximal subspaces in a different way? Like I'm not sure that.
Yeah, I mean, you just used the fact that you counted the number of subspaces of dimension R.
Right.
And then you say, oh, but I'm not going to use that. If R is bigger than R is bigger than t over 2, then I'm not using the obvious bound because I know there are 0.
I see.
The special one has to be orthogonal to itself.
Yeah, no. So we thought about it. It didn't work for us, but maybe because what I wrote, like if you think about it, we counted the number of clicks like almost precisely, right? It's almost precisely, just up to the ordering. So you need to divide by t factorial or something, right?
I'm confused about that because it doesn't seem likely
because we didn't count a vector space. We just counted like t elements from some vector space of dimension at most zero, right?
Yeah, but one of the terms is the
is a basis. One of them is a basis. Right. Yeah. So in theory, so what we lost, we only lost something of the form like at most t factorial or something like that. This is the only term that I see that you can gain back, maybe.
I think that doesn't seem right because I can't see.
No, maybe I'm missing something. I don't know. Like,
because you could have said, doesn't the same argument says that your count is correct when the rank is bigger than t over 2, but when the rank is bigger than t over 2, you know that there are 0 such spaces.
Right.
So I suspect that there is some. I don't think the real thing can be discontinuous in that way, and then maybe you can count it near a bit less.
You see, I will think about it because I think that the count is quite precise if you assume that the rank is exactly t over 2. That's what I'm saying. That you don't lose much.
No, because you didn't use that. You didn't use it vectors were even, which in your bound, and you sort of, that feels like it's a factor half each time, but it's not, because if you look for a rank t over 2 plus 1, then it also feels like it's a chance of being half of being even each time, but actually, you know, the chances are all even is 0. So
I see. Okay, I see your point. Okay.
I think the sort of proper count would be the number of rank R subspaces, and then you choose the basis. But now, when you look at the number of rank R subspaces that are orthogonal to themselves, then the counting will be quite different as you get near the t over 2.
I see. Oh, yeah, it's a good point. Okay, now I see your point. Sorry.
Okay, any other questions? Okay, so maybe I will stop the recording and then let's thank Asaf again for a great talk.